Good morning, and thank you for joining us. Today's presentation is Method Optimization Series, Purge Parameter Selection. Amy Nutter is our presenter today. She is an applications chemist. I wanted to let you know that we will be taking questions throughout the presentation, so feel free to submit those using the question function on your toolbar. And I'm going to go ahead and hand it over to Amy.
All right, thank you very much for the introduction. Like she said, I'm Amy Nutter. I'm an applications chemist here at Teledyne Tekmar. And today I will be discussing purge parameters for method optimization. All right, first we will discuss the fundamentals of purge and trap and purge parameters, and then purge gas selection with data from an alternative purge gas. And then I'll go into purge volume by flow rate and time with associated data. And then we'll wrap up with data from in-vial versus traditional purge techniques. So just so everyone is on the same page, let's go over exactly what purge and trap is. Purge and trap is a technique used to improve the sensitivity of volatile samples analyzed by a GC and their detectors, such as a mass spec, and go beyond the capabilities of other purge preparation methods like static headspace or liquid injections. Now let's get into how this works. Purge and trap works on a purge equilibrium theory or disequilibrium theory. Volatile compounds of interest in a liquid sample migrate from the liquid or solid phase to the gaseous phase, and then the gas is swept away onto the trap, where it is then concentrated and released to the GC. In the case of static headspace, seen on the left, samples come to equilibrium and the compounds of interest go from the liquid to the gaseous phase, and once that equilibrium is reached, meaning no more net transfer is occurring, an aliquot of that headspace is taken and analyzed. If not enough sensitivity is reached during this analysis, purge and trap can improve on the sensitivity by continuously replacing the headspace so that there is always a disequilibrium, meaning that there is always a higher concentration in the liquid phase than in the gaseous phase. So there is always a net movement of compounds of interest from the liquid to gas. Then the compounds are then concentrated onto the trap and released into the GC. A basic purge and trap consists of four main parts. The most important is our 6-port valve we see there in the middle, because it directs all the flows through the purge and trap system. It moves inert, clean gas that purges the sample and then moves that purged sample from the trap to the GC. Another component is the sparger, which is the glassware on the front of the instrument that a liquid sample gets transferred into and purged. But with our newest instruments, samples can also be purged inside of the sample vial. From there, during desorb, gas sweeps the compounds of interest onto the analytical trap, where they are then concentrated before being introduced into the GC via the heated transfer line. So that was a very basic diagram, basic breakdown of what is going on during the purge and trap phase. But overall, there are a lot of parameters that can determine purge efficiency. For example, there are different traps that you can select from, and for more information about this, that was the topic of our previous webinar in this series, so be sure to check that out if you're interested. We also consider sample volume, meaning the amount of sample that you purge in the sparger or in your sample vial. And then next, we either purge in the vial, which keeps large particulates, especially found in soil samples, from contaminating the instrument and the GC. And then there's the traditional way of purging in the sparger, which gas type and volume you use, such as the amount of time you are purging with the gas and the flow rate. We also consider dry purge, which can help with moisture control, and the desorb, or the amount of time it takes to transfer the compounds of interest from the trap to the GC. A shorter desorb time might cause a loss of heavy eluter compounds, and too long of a desorb might introduce a lot of water onto the GC. For this webinar, we will be discussing the in-vial versus traditional purge methods or techniques and purge gas type and volume. Now let's really get into purging. The purge of purge and trap is the process through which the VOCs are stripped out of the sample for analysis. Purging allows us to collect only the volatile portion of the liquid or solid sample, while liquid portions are retained in the glassware and not transferred to the GC inlet. Purging also facilitates sample concentration without the use of expensive or toxic solvents, and some VOCs don't even work well with solvents anyway. These are the characteristics of a gas that make it a great gas for purging VOCs. So it must be inert, meaning it cannot react with VOCs or anything else in the sample. It cannot be combustible or unstable, such as hydrogen. For our instruments, during our desorb phase, the trap is closed off and heated, which can build up pressure, which means problems for such a combustible compound such as hydrogen or oxygen. Hydrogen can be used as a GC carrier gas, for example, because when we are in the bake phase, the instrument doesn't really build up pressure, so it should be fine. But also, a purge gas must be free of VOCs. Usually the standard is 5/9 pure gas or 0.99999. You don't want to contribute to the total VOCs in your sample collected and create false positives or contaminate your blanks. So helium is the traditional carrier gas of choice because of its superior inertness, stability, and compatibility with GCMS. But it can be somewhat expensive and occasionally difficult to get. Nitrogen can be a good alternative to helium because of its similar inertness, low cost for cylinders, and it has the ability to be produced from a generator. And it's really easy to get 5/9 pure nitrogen gas. Because nitrogen is a large molecule, it goes through the GC column first and fast, which can occasionally have a minor effect on the purge efficiency and the MS vacuum during desorb and pump down. But it often provides more than adequate purge efficiency for compounds of interest under standard EPA parameters. Now let's get into some data. Purge and trap, these are the purge and trap parameters for the Lumen Aquatech 100. And this is an app note done with 524.3 with helium as the purge gas and 524.4 with nitrogen as the purge gas. Helium remains the carrier gas in the GC. I just want to point that out. And I also want to point out that for both methods, we used an 11-minute purge time and a purge flow of 40 mils per minute. So there's your purge time and flow rate. And we used 0 minutes dry purge and 1 minute desorb. And like I mentioned before, nitrogen was just used as a purge gas. Helium was the GC carrier gas. Here are GC parameters for 524.3. Here, just want to point out the column that we use is a 20 meter, 0.18 millimeter inner diameter. It's a pretty standard column we use for most of our app notes, and that our mass spec is on full scan. Very similar parameters for our 524.4 method. All right, and here are the results for the gases, our front compounds that come out. And if you want to check out the full application note, we have it available on our website. The two are app note AN 1706 and AN 1707. On the top left, we have our nitrogen as our purge gas, and the bottom right is helium as our purge gas. As you can see, both are very linear, have passed all method parameters for our MRL confirmation, and then the MDLs look great. And as we move on to the mid-range compounds, again, we see very linear, great MDLs. The MR conformation passes all method parameters, and our recovery continues to look great. And here we have the results for the late eluters, or the heavy compounds at the end. Again, very linear and passed all method parameters for the MDL and our MRL conformation with great recovery. So our standard EPA method requirements were easily met with both purge gases, and that's even with a calibration that went as low as 0.5 ppb and up to 50 ppb. We saw excellent sensitivity from the gases all the way to the heavy compounds at the end. This can be attributed to the sensitivity of modern mass specs, as well as the use of helium as the carrier gas in the GCMS. Nitrogen is an excellent purge gas for those who want to reduce operating costs and want to buffer against uncertain helium supply, and those who don't want to compromise chromatographic quality or invest development time into an alternative carrier gas method. Right. When considering purge volume, first we want to look at the flow rate. Basically, how many minutes or the amount of time we are purging and how fast, which would be the flow. A fast flow means more purge gas is used in the same amount of time, and a really aggressive flow can cause pressure issues or push compounds of interest deep into the sorbent bed of the trap. We also want to look at purge time. The longer we are purging, the more purge gas we are using, and if we purge for too long, it can waste a lot of gas and push our compounds of interest deep into the sorbent bed of the trap also. Therefore, as our purge volume and time are increasing, they get to the point where the response starts to plateau, and eventually you start to lose response because those compounds are getting stuck on the sorbent bed of the trap, which can lead to a waste of time and gas, which means a waste of resources. For our purge volume comparison for 524.4, these are the parameters used for the Lumen and Aquatech 100. Here we are looking at different volumes of our purge gas. For our purge parameters, we have a low volume of purge gas. We have our 524 method in the middle, which is our pretty standard EPA 524.2 method. And then we have a high purge volume on the right. And I also want to point out that each method parameter has different purge times and purge flows. And as you can see, the one in the middle is your pretty standard 524.2 method, while the other two on the left and right are playing with the limits of 524.3 parameters in order to decrease each time for the analysis. As you can see here, each total time for the analysis is different for each method. And also for our GCMS parameters, again, we're using that standard 20 meter, 0.18 millimeter inner diameter column with helium as our carrier gas, and we were using full scan mode again on the mass spec. So here's the data we have here for our gases, our front compounds, and as you can see, some of the water-soluble compounds need a little bit more time to desorb, but compounds that are less affected by water seem to be pretty consistent from method to method, whether it being the low volume of purge gas used or the high volume of purge gas and flow rate used. And moving on to more mid-range compounds. Again, some of the compounds are pretty consistent across the board. Some for the low volume and the high volume need a little bit more desorb time. But the MDLs look great for each. All right, again, if you stick to a pretty standard 524.2 method, your RSDs look really great. Again, for some of those compounds, they need just a little bit more time to desorb. All of these look pretty great. The MDLs look good. And moving on to those heavier compounds, again, some of them need a little bit more time to desorb. But as you can see, the middle column with the 440 mil purge flow, you can see that the RSDs look great, and that's your standard 524.2 method. And getting into the heavier compounds, some with the low flow and the high flow definitely needed some more time to desorb. And our heavier compounds here at the end, same as before. But by varying the EPA 524 method purge flow rate and volume, the purge portion of the purge and trap cycle time can be cut in half. As a result, more samples can be processed during a typical calibration cycle without analytical shortcomings, and depending if you can play with that desorb time too. The takeaway is that potentially the gases can be affected at a higher purge flow rates, and the heavier compounds, like in the back end, can decrease with shorter purge times. But if you stay within the flows and the time ranges recommended for the 524.2 method, the data should look fine. But if you're willing to accept some minor changes, you can drastically reduce the runtime for 524.3 and boost productivity in your lab. Now for our last topic of this webinar, we will be discussing the In-Vial versus traditional purge. So this was done with the new Atomics XYZ and the 8260 EPA method. So on the left, we have our 8260 soil method with the Atomics XYZ. It actually purges in the vial. So this will act as our in-vial samples, versus on the right, we have our water method, which uses the traditional Sparger purge. And I'd just like to point out that these are some pretty default method parameters, 11-minute purge with 40 mils per minute purge flow. And here we have the GC-MS parameters. Again, using that same column, 20 meter, 0.18 millimeter inner diameter, helium as the carrier gas, and we're using our full scan mode again. All right. And again, our in-vial purge is shown on the left, and our traditional purge is shown on the right. And in this calibration curve, for both the soil and the water, went all the way down to 0.5 ppb and went as high as 20 ppb. A great example of the purge efficiency of a traditional purge in the Sparger is dichloro-difluoromethane. And as you can see, the RSD is a little bit higher for that in-vial purge. And that is because in-vial purges create large bubbles, and it doesn't really create a water column for the compounds of interest to be efficiently or effectively purged. The smaller bubbles formed in the Sparger create a tall, narrow water column for those compounds to be efficiently purged. But again, we do this in-vial purge for soil samples and samples with large sediments so that we don't contaminate the instrument or cause carryover issues. Therefore, we do accept a little less purge efficiency in order to keep the system clean. But as you can see, looking at the rest of these compounds, the RSDs look great. We're passing all method parameters. The MDLs are slightly higher for the In-Vial purge in the soil method, but overall, we're passing all method parameters here. Getting more towards mid-range compounds, still really great RSDs, the recoveries look great, and our MDLs are passing. And even into some heavier compounds, we've got our RSDs still looking really great and our MDLs passing. Further look into some heavier compounds. Still recovering great with our MDLs looking good and our RSDs passing. And our heaviest compounds there at the end. The method requirements were easily met for both the In-Vial and the traditional purge. We did see our MDLs and our In-Vial purge being slightly higher and an increased recovery or percent accuracy for our traditional purge, but both passed our method, our 8260 EPA method, and looked great. So I just want to thank you all for taking the time to join me for this webinar today. And just a heads up, we now have an online store available for your convenient shopping of all of our products. And now we will go on to answer some questions, but if you have any questions that come up in the future, you can email me directly at my email address there. Or if you have any technical support questions, please feel free to email the technical support address. Thanks again. Have a great day.